Look at your wristwatch. The tiny mechanism on your arm is keeping a kind of time that exists nowhere else in the universe. A time stitched precisely to this planet, this gravity, this distance from anything truly massive. Move that watch toward a black hole, and its hands begin to disagree with every other clock ever made. Edge nearer, and the disagreement grows monstrous. At the horizon itself, the watch and the universe stop sharing the same word for now. Tonight, we travel from your wrist to the edge of the universe's most extreme objects and discover why every truth about time you carry is only locally, provisionally correct. Before we dive in, if you love exploring the mysteries of space-time as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. Time, as you experience it in this moment, feels like the most self-evident thing in the world. It flows forward. It moves at the same rate whether the room is warm or cold, whether you are exhausted or rested, whether you are standing on a mountaintop in Nepal or sitting at the bottom of a mine shaft in South Africa. You have never had any real cause to question this. Every clock you have ever owned has agreed with every other clock, with intolerances so small they were invisible to your daily life. Every appointment kept, every heartbeat counted, every breath drawn, all of it unfolding inside the same steady current, the same forward-moving river. And you come by this belief honestly. It is not merely intuition. The greatest physicist of the pre-modern world codified it, formalized it, and gave it the full weight of mathematics. Isaac Newton, writing in 1687 in his Principia Mathematica, described time as absolute. Absolute, true and mathematical time, he wrote, of itself and from its own nature, flows equably without relation to anything external. Time for Newton was the skeleton of the universe, a fixed, unchanging backdrop against which everything else occurred. Objects moved through time the way fish move through water. The fish can dart and turn and slow, but the water's nature is not altered by anything the fish does. Mass did not change time. Speed did not change time. Gravity, that most fundamental and tangible of forces, was simply a pull between bodies, a long-distance interaction, and it touched clocks not at all. Every second, in every corner of the cosmos, was the same second. Identical, interchangeable, absolute. Newton was not wrong to think this. At the speeds and scales accessible to 17th century physics, cannonball trajectories, pendulum clocks, planetary orbits, his framework matched the observable world with extraordinary precision. It held, unchallenged, for more than 200 years. It is still what most people instinctively believe, because for most human purposes, it is accurate enough to build bridges, navigate oceans, and set a morning alarm. The error it contains is so small, so invisible at everyday scales, that a person could spend an entire lifetime inside it and never encounter a moment where the approximation revealed itself as anything less than truth. But here is what almost nobody tells you about Newton's absolute time. It is an approximation, a very good one, useful for almost every practical problem a human being has ever faced, and also deeply, fundamentally wrong. The universe does not have a single clock. It does not run on a universal second. Time is not a fixed backdrop against which events occur. It is a dimension of space-time, and like the other dimensions, it can be stretched, compressed, and curved by matter and energy. Once you truly grasp what that means, the wristwatch on your arm becomes something you will never look at the same way again. It stops being a window into universal time and becomes something far stranger, a record of the particular, local, gravity-soaked conditions of this specific place in the cosmos. This first revelation did not arrive from a telescope pointed at a distant star. It arrived from a thought experiment. In 1905, a 26-year-old patent clerk working in Bern, Switzerland, published a paper that would quietly dismantle Newton's absolute time. His name was Albert Einstein, and the paper, on the electrodynamics of moving bodies, proposed something that seemed on the surface almost too strange to take seriously. He argued that the laws of physics must be identical for all observers moving at constant velocity relative to one another. Not approximately identical, not practically identical for most measurements. Mathematically, fundamentally identical in every case. And if that principle held, a breathtaking consequence followed. The speed of light in a vacuum must be the same for every observer, regardless of how fast those observers are themselves moving. Pause on that for just a moment, because it is genuinely disorienting. If two observers are moving relative to each other, one standing still, one rushing past at half the speed of light, and both of them measure the speed of a beam of light passing between them, they get the same number, the same speed. The person standing still measures 300,000 kilometers per second. The person moving at half the speed of light also measures 300,000 kilometers per second for that same beam. Not 1.5 times the speed of light, adjusted for motion. Exactly the same. Always. This is not intuitive. Every other kind of speed in our ordinary experience compounds. Throw a ball forward from a moving train, and the ball moves at the speed of your throw plus the speed of the train, relative to the ground. That is the rule everything else follows. Light does not follow this rule. And from that single anomaly, everything changes. If light speed is constant for all observers, then time cannot be. Two observers moving relative to each other will measure different durations between the same two events. A clock on a fast-moving spacecraft will tick slower than a clock on the launch pad it left behind. Not because the spacecraft clock is broken or poorly calibrated, but because time itself dilates. Stretches. The faster you move through space, the more slowly you move through time. They are traded off against each other, two dimensions of the same underlying geometry. Feel what that means in your body for a moment. An astronaut aboard a spacecraft traveling at 80% of the speed of light does not merely appear to age more slowly to an observer watching from Earth. The astronaut genuinely, biologically, ages more slowly. Their cells divide at a slower rate. Their heartbeat is slower, not because their heart is under stress, but because the second itself is longer for them than for someone standing on the ground. They return home measurably, physically younger than the twin who stayed behind. This is not a metaphor. This is not a rounding error. It has been confirmed, with atomic clocks flown on commercial aircraft in the 1971 Haffel-Keating experiment, with clocks aboard satellites, with subatomic particles called muons that survive far longer than their rest frame decay time should allow when they are traveling close to the speed of light, because their internal clocks are running slow. Time dilation from velocity is real. It is measured constantly. It is built into the technologies you depend on. This was Einstein's special relativity, and it dismantled the idea of universal time at a stroke. But it applied only to a specific case, observers moving at constant velocity. It said nothing about acceleration, nothing about the most pervasive force in the universe, nothing about gravity. The next 10 years of Einstein's life were devoted to extending his framework to cover those cases. It was, by his own account, the most difficult intellectual work he ever undertook. The mathematics required went far beyond what special relativity had demanded. But in November 1915, in a series of lectures and papers that rank among the most consequential documents in scientific history, Einstein published his general theory of relativity. General relativity told a completely different story about gravity than Newton had told. In Newton's account, gravity was a force, an invisible attraction transmitted across empty space, pulling masses toward each other. In Einstein's account, there was no force at all. Instead, mass and energy curve the very fabric of space-time itself, and what we call gravity is simply the motion of objects following the straightest possible paths through a curved geometry. The Earth does not reach out and pull the Moon. The Earth bends space-time around itself, and the Moon, moving through that curved space-time, follows the curve. It is coasting along the gentlest possible path, a path that, from outside, looks like an orbit. You have probably encountered the rubber sheet image used to illustrate this. Press a heavy ball into a stretched sheet of rubber, and the sheet dimples around the ball. A marble rolled nearby curves inward, not because the ball is pulling it, but because the marble follows the geometry of the dimpled surface. That image captures the spatial part of the story well enough. But here is where the standard picture leaves something crucial out, something that changes everything. It is not only space that curves, time curves too. A clock sitting deeper in a gravitational field, closer to a massive object, lower in what physicists call a gravity well, runs more slowly than a clock sitting farther away, higher up, in a weaker region of the same field. Not slightly, not as a rounding error, measurably, verifiably, in ways that propagate upward into every technology that depends on precise timekeeping. The deeper you sit in a gravity well, the slower your clock ticks relative to one hovering far above you in weaker gravity. And the more massive the object creating the well, the more violently it curves space-time, the more pronounced the effect. This is gravitational time dilation. It is the phenomenon we will follow tonight from its most gentle, barely perceptible form, here on Earth, all the way to its absolute extreme, at the boundary of a black hole. Here is the mechanism, stated as plainly as language allows. In general relativity, time and space are not separate things. They are two aspects of a single unified structure, space-time. Mass bends that structure. And because time is woven into the structure, mass bends time. Closer to a mass means deeper in the curve, and deeper in the curve means slower time. The relationship is not approximate or metaphorical. It is described by exact equations, and those equations have been tested repeatedly at multiple scales, with results that match predictions with extraordinary precision. The clearest way to feel this, to move it from abstraction into something with weight, is to think about clocks at different altitudes. Not in outer space, not near some distant star, but here on Earth. A clock sitting on the floor of a room is in a slightly stronger gravitational field than a clock sitting on a shelf 5 meters above it, because the floor is 5 meters closer to the center of the Earth. The difference is so small it would take billions of years to accumulate to a single second. But the difference is real. The equations predict it. And as of 2010, atomic clock technology became sensitive enough to measure it directly. Researchers at the National Institute of Standards and Technology in Colorado confirmed gravitational time dilation over a height difference of just 33 centimeters, roughly the height of a large book, less than the length of your forearm. But the first definitive laboratory proof arrived decades earlier in a far simpler apparatus. In 1959, physicists Robert Pound and Glenn Rebka conducted an experiment at Harvard University that would become one of the landmark demonstrations of general relativity. They installed a source of gamma rays, high-frequency electromagnetic radiation produced by radioactive iron, at the bottom of a tower 22.6 meters tall. At the top of the tower, they placed a detector. The experiment was designed to measure something almost impossibly subtle: whether the gamma rays changed frequency as they climbed from the bottom of the tower to the top. Here is why that frequency shift matters. A gamma ray can be thought of as a clock of sorts. Each complete oscillation of its electromagnetic wave constitutes one tick. A clock at the bottom of the tower is deeper in Earth's gravitational field, and general relativity predicts it will tick more slowly than a clock at the top. If the gamma ray is generated by a clock running slowly at the bottom, then from the perspective of the faster running clock at the top, the ray will appear to arrive with a slightly lower frequency. Its ticks will seem slightly stretched out, slightly reddened in frequency. The technical term for this is gravitational redshift. The ray climbs out of the gravity well and loses a tiny fraction of its energy in doing so, shifting toward lower frequency, toward the red end of the spectrum. 22.5 meters, not 22 light years between galaxies, not 22,000 meters between a satellite and the ground. Roughly 22.5 meters, about the height of a 6-story building. Pound and Repka measured exactly the redshift general relativity predicted to within about 10% on first measurement and to within about 1% after refinements. Gravity changes the rate of time measurably over the height of a 6-story building. That result should feel strange, because it is strange. The floor beneath you and the ceiling above you are not at the same time. The difference is infinitesimal in any practical sense, but it is real, it is measured, and it has been confirmed by every precision experiment conducted since. The most familiar real-world consequence of this involves the GPS satellites orbiting approximately 20,000 kilometers above the Earth's surface. Those satellites carry atomic clocks. Because they orbit in weaker gravity than the clocks on the ground below them, their clocks run faster, by about 45 microseconds per day, due to gravitational time dilation alone. There is also a competing effect from their orbital velocity, which causes their clocks to run somewhat slower due to the velocity-based time dilation Einstein identified in 1905. The net result is that satellite clocks run faster than ground clocks by about 38 microseconds per day. That sounds trivial. But because GPS systems calculate your position by measuring the travel time of radio signals from multiple satellites, a 38 microsecond per day clock error would translate into a position error of roughly 11 kilometers per day. Without relativistic corrections built directly into the system, GPS would be useless for navigation within hours of operation. The engineers who designed GPS had to take Einstein's equations seriously. Time dilation is not a philosophical curiosity. It is a condition the modern world compensates for every single day. Take stock of where we are. Newton's absolute time, the universal equably flowing river of seconds that was the backbone of classical physics for 200 years, has been retired. In its place stands Einstein's far stranger picture: time as a dimension of space-time, woven together with the 3 spatial dimensions into a single fabric that responds to mass, that curves around every object in the universe, that runs at different rates depending on how deep you sit inside a gravitational field. We have the Schwarzschild solution, derived in late 1915 by Karl Schwarzschild, while serving with the German artillery on the Russian front, sent to Einstein from the battlefield, published in early 1916 and followed by its author's death from pemphigus only months later, which describes the exact geometry of space-time around a perfectly spherical mass, and which predicts that at a certain critical radius from a sufficiently compact mass, space-time becomes so strongly curved that an event horizon forms, while the true singularity, where current equations predict infinite curvature, lies deeper inside at the center. We have Pound and Rebka's 1959 to 1960 measurement demonstrating that 22.6 meters of vertical distance is enough to produce a detectable difference in time. Everything we have covered so far is foundation, established, measured, beyond reasonable scientific dispute. Now we begin to move. The wristwatch on your arm tells you the time here, in this gravity at this distance from this planet. As we travel outward, through increasing distances, toward increasing densities of mass, toward the most extreme geometry the universe is known to produce, the watch will begin to diverge from every other reference it could possibly have. The divergence begins gently, almost imperceptibly. Then it becomes dramatic. Then it becomes something for which ordinary language has no comfortable home. The journey from your wristwatch to the event horizon of a black hole is one of the most consequential passages in all of physics. And it begins with a question we have not yet answered. What exactly is a black hole? And why does the space-time around one behave so differently from the space-time around the Earth beneath your feet? To understand what happens to time near a black hole, we first need to understand what a black hole actually is, not as a cultural shorthand or cinematic special effect, but as a physical object with a precise definition embedded in the geometry of space-time. A black hole is a region of space where the gravitational field has grown so extreme that the escape velocity exceeds the speed of light. In more concrete terms, if you were standing at the surface of a black hole's event horizon and attempted to throw something outward, even a beam of light, with any conceivable amount of force, that object would not escape. It would fall back. It would fall inward. Everything falls inward, always from that boundary. Not because some force is dragging it down, but because the geometry of space-time inside the horizon contains no future direction that points outward. You cannot move toward the outside any more than you can move backward through time. Both directions have been closed by the curvature of the geometry itself. This is not an exotic edge case. It is what the equations of general relativity predict for any mass compressed below a critical density. And it is a prediction the universe, it turns out, fulfills abundantly. The most familiar pathway to a black hole runs through the death of a massive star. Every star visible in the night sky is engaged in a lifelong equilibrium, the outward pressure of nuclear fusion in its core pushing against the inward crush of its own gravity. For a star like the Sun, this balance will last approximately 10 billion years. For more massive stars, the fuel burns faster and the life is shorter. A star 10 times the mass of the Sun exhausts its core in only a few tens of millions of years. When the fuel runs out, the balance collapses. The core falls. For low-mass stellar remnants, a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being crowded together, arising from a principle in quantum mechanics that forbids two electrons from occupying the same quantum state, can halt the collapse, producing a white dwarf, a body roughly the size of Earth, but carrying the mass of the Sun, slowly cooling over billions of years. In 1931, Indian-American astrophysicist Subrahmanyan Chandrasekhar calculated the upper mass limit for this stability, approximately 1.4 times the mass of the Sun. Above that threshold, the Chandrasekhar limit, electron pressure cannot hold. The collapse continues, compressing electrons and protons together into neutrons, producing a neutron star roughly 20 kilometers in diameter, often spinning many times per second, and in some cases, hundreds of times per second. So dense that a single teaspoon of its material would weigh approximately 1 billion tons on Earth. Neutron stars have their own pressure limit, somewhere between 2 and 3 solar masses, above which no known force can arrest the fall. Above that limit, the collapse is total. The core falls past neutron star density without stopping. According to general relativity, it falls without limit. What remains is a singularity, a point of theoretically infinite density, surrounded by the event horizon, the invisible, immaterial boundary from which no signal of any kind can emerge. Whether a true singularity exists at the center remains a question at the frontier of physics. In 1965, mathematician and physicist Roger Penrose published a proof that singularities were not merely possible within general relativity, but mathematically unavoidable under very general conditions of gravitational collapse. His paper established that once collapse begins past a certain threshold, under the assumptions of classical general relativity, no known conventional mechanism could prevent singularity formation once collapse passed a critical threshold, unless new quantum gravitational physics intervenes. That something beyond is likely quantum gravity, a theory that remains unfinished. For his work on singularities, Penrose received the Nobel Prize in Physics in 2020, 55 years after the original proof was published. American theoretical physicist John Archibald Wheeler coined the term black hole in 1967, replacing earlier, more cumbersome descriptions. The name carries precisely the right implication: a region that has become, from the perspective of the outside universe, an absence, a hole where a star once stood. Black holes exist across an enormous range of masses. Stellar mass black holes, formed from collapsing stars, typically range from about 5 to roughly 100 solar masses. Supermassive black holes, found at the centers of most large galaxies, range from millions to billions of solar masses. The one at the center of the Milky Way, Sagittarius, A star, contains approximately 4 million solar masses and sits about 26,000 light-years from Earth in the direction of the constellation Sagittarius. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a luminous ring of hot plasma swirling around a central darkness, matching the theoretical predictions of general relativity with remarkable fidelity and confirming, beyond any residual doubt, the presence of a supermassive black hole at our galaxy's core. For the journey ahead, picture a stellar mass black hole, perhaps 20 times the mass of the Sun, with a Schwarzschild radius of roughly 60 kilometers. It is not glowing. It has no surface. In the darkness of space, with no nearby gas or dust to illuminate its presence, it would be effectively invisible. A sphere of geometric absence, detectable only by its gravitational influence on nearby objects or by the faint distortion it produces in the light of background stars. This is where we begin. Take a moment here to look back at the path. We have left Newton's absolute time behind, replaced it with Einstein's spacetime, confirmed gravitational time dilation at the scale of a Harvard tower, and arrived at the edge of a black hole's domain, a region where space-time curves not gradually, but with increasing ferocity as we draw closer to the center. The event horizon awaits. But first, we must understand what the space leading to it actually looks like from a distance, and what time is already doing in that space before we arrive. The opening of the well starts gently, almost imperceptibly, but it has already started. Everyone knows what a black hole does. It is a cosmic vacuum cleaner, a ravenous, insatiable void that pulls in everything around it, swallowing planets and stars and gas and light without discrimination, consuming endlessly until nothing within reach survives. The image is pervasive. It has narrative weight. It has the backing of countless documentaries and popular accounts, and it contains a genuine fragment of truth. Things that cross the event horizon do not return. That picture is almost entirely wrong about what happens at large distances. From thousands of Schwarzschild radii away, hundreds of thousands of kilometers from the event horizon, in the case of our 20 solar mass black hole, the gravitational field is identical to that of any star with the same mass. Completely, mathematically identical. If the Sun was somehow compressed to its Schwarzschild radius of about 3 kilometers and became a black hole this moment, Earth would not spiral inward. Earth would continue in its present orbit, unchanged. The Moon would keep its orbit. The other planets would keep theirs. Nothing would be pulled in that was not already falling before the transformation. What makes a black hole different from an ordinary star of equal mass is not the strength of its gravity at large distances. It is the absence of a surface and the existence of the event horizon at a very small radius. An ordinary star occupies a physical extent far larger than its Schwarzschild radius. If you fall toward a star, you hit its outer atmosphere, then its surface, at a radius vastly greater than the point where the Schwarzschild geometry becomes extreme. The surface stops you. It provides a floor. The region of genuinely violent space-time curvature, the region where gravitational time dilation becomes dramatic, is buried inside the star's own mass and inaccessible. With a black hole, the surface is gone. You can fall all the way to the event horizon without encountering any material resistance. And because all of the mass is compressed inside the Schwarzschild radius, the geometry outside is exposed. Bare, accessible, traversable. Nothing stands between you and the boundary except space. So from far away, thousands of Schwarzschild radii distant, your wristwatch and a reference clock at infinity would differ by a fraction so small it would take instruments of extraordinary precision to detect it. Time dilation at this range is real, present in the equations, confirmed by the Schwarzschild metric. But it is negligible in any practical sense. You are in the shallow part of the well. Here is a question worth holding on to as we travel closer. What would you see if you watched an object fall toward the event horizon from this distance? This question, followed carefully to its conclusion, inverts almost everything obvious about approaching a black hole. It splits into two radically different answers depending on who is asking: the person watching from far away or the person actually falling. Both answers are correct. Both are physical. And yet they describe what appears on the surface to be an entirely different sequence of events. Plant this question here. We will return to it with full attention when we are close enough for the difference to be vivid. Two concepts are essential for what follows, and physicists have given them names worth knowing. The first is proper time, the time measured by a clock that travels along a specific path through space-time, the time that an observer on that clock actually lives through, what ticks on your wrist as you move. The second is coordinate time, a bookkeeping tool used by a distant, stationary observer to label events, roughly analogous to a clock hovering far from all massive objects in essentially flat space-time. In that flat region, proper time and coordinate time agree. Your wristwatch and a distant reference clock tick in unison, and the difference between them is undetectable. As you descend toward the black hole, these two times begin to separate. Your proper time, your felt experience of duration, continues flowing normally from your perspective. Your heartbeat is regular. Your thoughts are clear. But coordinate time, the time the distant observer assigns to your location, runs increasingly fast compared to your proper time. The observer watching your transmitted signals sees them arriving at progressively stretched out intervals, as if your clock were gradually slowing. The deeper you fall, the more pronounced this divergence. Consider what this means for light. A photon climbing outward from a strong gravitational field expends energy doing so, not by slowing down, since the speed of light remains constant, but by shifting frequency. Light climbing out of a gravity well shifts toward lower frequency, longer wavelength, the red end of the spectrum. This is gravitational redshift, and it is the optical signature of the same phenomenon as time dilation. If you emit a light pulse from the bottom of a gravity well once per second by your own clock, a distant observer receives those pulses at intervals greater than 1 second by their clock, because your clock is running slower. The redshift of the light is a direct measure of the time dilation between you and the observer. They are the same effect, seen from different angles. At this distance, the redshift in signals from your position is too small to measure without exquisite instruments. But it is there, and it will grow. Now step inward. We are approaching the photon sphere, a region at exactly 1.5 times the Schwarzschild radius from the center. For our black hole with a Schwarzschild radius of 60 kilometers, the photon sphere sits 90 kilometers from the center. At this distance, the curvature of space-time has become so extreme that light, which always follows the straightest possible path through whatever geometry it encounters, can travel in a perfect circle. A photon at precisely this radius, moving at precisely the right angle, orbits the black hole indefinitely, tracing a closed loop through curved space-time. The photon sphere is not a stable orbit. It is an unstable equilibrium, a knife's edge. Any small perturbation sends a photon either drifting slowly outward and eventually escaping, or drifting slowly inward and being consumed. Real photons do not remain here for long, but the radius itself is mathematically precise, its effects physically real, and standing at this distance, hypothetically suspended 90 kilometers from the center, produces one of the most extraordinary visual environments physically possible. Look around. The universe behind you has been compressed and redirected. Light from stars distributed across an entire hemisphere of sky has been bent by the black hole's gravity, drawn inward, redirected, so that it arrives from unexpected angles. The entire sky behind you has been gathered into a bright ring ahead of you, a luminous band encircling the dark sphere's shadow. Stars appear in positions they do not occupy. Galaxies that sit directly behind the black hole appear as arcs of light, their shapes distorted by the curvature of space-time between them and you. You would see multiple images of the same star, bent around the black hole's profile along different paths. In principle, with perfect patience and perfect geometry, you could see the back of your own head. Light that left your body orbited the photon sphere and returned to your eyes. You would see the universe ahead of you. You would see the universe behind, bent into a ring around the dark sphere. You would see galaxies compressed into glowing arcs, their shapes remapped by geometry. Nothing in human experience prepares you for a sky like this one. This bending of light has a name: gravitational lensing, borrowed from optics, though the mechanism is not refraction through glass. It is the natural consequence of light following curved spacetime. The principle was first confirmed observationally during a solar eclipse in May 1919, when British astronomer Arthur Eddington led an expedition to Principe, an island off the western coast of Africa, to photograph stars whose apparent positions should shift as the sun's gravity bent the light passing near it. They did shift by almost exactly the amount Einstein had predicted. The result made international news. The mechanism operating near a black hole is the same in nature, staggeringly greater in degree. Now consider what time is doing at this radius. The Schwarzschild metric gives a precise prediction. The ratio of proper time to coordinate time at 1.5 Schwarzschild radii is the square root of 1 minus 1 over 1.5, which simplifies to the square root of 1/3, approximately 0.577. The clock here ticks at about 57.7% of the rate of a clock at infinity. Every 10 seconds on your wristwatch correspond to roughly 17 seconds on the distant reference clock. Every hour of your subjective experience corresponds to 1 hour and 43 minutes in the universe you departed. This is no longer negligible. This is no longer the domain of atomic clock corrections or GPS software patches. If you spent 1 hour at this radius by your own measure, 1 hour of breathing, thinking, watching the distorted sky, and then somehow climbed back to the distant universe, you would return younger by 43 minutes than the universe expected. Your colleague who stayed behind would have aged nearly 2 hours while you aged 1. And we have not yet reached the event horizon. We are still outside it by half a Schwarzschild radius. What is producing this effect at the level of space-time geometry? The mechanism runs deeper than the rubber sheet analogy captures. In general relativity, time and space are not separate bookkeeping systems, but two aspects of a single four-dimensional structure. You are always moving through space-time. Always, even when you are physically stationary, you are moving through the time dimension. The geometry of space-time in a gravitational field curves the time axis. What registers as 1 second of proper time in a deep gravity well corresponds to more than 1 second of coordinate time higher up. The curvature has stretched the relationship between your local time and the time of the universe outside. You are not experiencing time incorrectly. You are experiencing it correctly for your location. It is the universe outside that is ticking faster, from your perspective, because it is in a shallower region of the geometry. You feel nothing unusual, no sensation of slowing, no heaviness in your thoughts. Your heartbeat feels steady. Your perception of the present moment is perfectly normal. The slowing is only visible in the gap, detectable only when you compare your clock to a clock at a different depth. And as we descend further, the gap grows. We are now at 3 Schwarzschild radii from the center, 180 kilometers from the core of our black hole. This radius carries a name in astrophysics, the innermost stable circular orbit, or ISCO. At any distance greater than 3 Schwarzschild radii, circular orbits around a non-rotating black holes are stable. A small perturbation, a nudge from a passing gas cloud, a slight asymmetry in the infalling material will cause the orbiting object to oscillate, to drift slightly, to precess, but not to spiral inward irrecoverably. The orbit survives. Inside 3 Schwarzschild radii, no stable circular orbit exists. Any object attempting to orbit at a smaller radius will find itself in an unstable configuration. The tiniest perturbation sends it spiraling inward without possibility of return. This is why the inner edge of an accretion disk, the swirling annulus of gas and dust that forms when material falls toward a black hole more slowly than a straight radial plunge, typically sits at or very near the ISCO. gas accumulates in the disk, loses angular momentum through turbulence and magnetic effects, gradually migrates inward from large radii, and radiates energy as it spirals toward the inner edge. At the ISCO, it reaches the last stable position. Below, it plunges. Matter arrives here at tremendous speed. Matter radiates here at tremendous temperatures. Matter is converted here, from the cool gas of interstellar space into plasma heated to tens of millions of degrees, at an efficiency no other known astrophysical process approaches. The numbers are worth sitting with. As gas falls from large radii down to the ISCO, it converts approximately 5.7% of its rest mass energy into radiation. This sounds modest. It is not. For comparison, hydrogen fusion in the cores of stars, the process that has powered the Sun for 4.5 billion years, converts less than 0.7% of rest mass energy to energy. Black hole accretion through the disk is more than 8 times more efficient than stellar nuclear fusion. For a rotating black hole, and many, likely most astrophysical black holes, appear to possess at least some rotation, the efficiency climbs still higher. In 1963, New Zealand mathematician Roy Kerr published the exact solution to Einstein's field equations for a rotating spherical mass. Schwarzschild's 1916 solution had described a non-rotating black hole. Kerr's 1963 solution described the geometry of space-time around a spinning one, and it contained surprises. The rotation drags space-time around the black hole in a phenomenon called frame dragging. The ISCO moves inward as the spin increases, and the accretion efficiency for a maximally rotating black hole approaches 42%. 42% of infalling mass converted to energy. Nothing in the known universe, outside the very early Big Bang, approaches this efficiency. This is why quasars outshine galaxies. A quasar, the intensely luminous nucleus of a distant galaxy, powered by accretion onto a supermassive black hole, can produce more light than 100 billion ordinary stars combined, not through any exotic new physics, but through the sheer efficiency of matter falling through the accretion disk, losing its gravitational potential energy to radiation on the way to the ISCO, and then plunging inward. At 3 Schwarzschild radii, the Schwarzschild metric gives us a time dilation factor, the square root of 2/3, approximately 0.816. Clocks here tick at about 81.6% of the rate of clocks at infinity. The effect is measurable and clear, but you still would not feel it from the inside. Your experience is normal. The universe above is ticking faster than you are, but only by comparison. Something else begins here, though. Something felt rather than calculated. Tidal forces. The gravitational pull on the side of your body facing the black hole is stronger than the pull on the side facing away. This differential, the gradient of gravity across the extent of your body, is trying to stretch you along the direction of fall. At the same time, the gravity on your left and right sides converges slightly toward the center, compressing your width. Stretch along the vertical, compress along the horizontal. This combination is tidal disruption, named by analogy with the ocean tides on Earth, produced by the Moon's differential pull across our planet's diameter. For a supermassive black hole like Sagittarius A star, the Schwarzschild radius is about 12 million kilometers, roughly 17 times the radius of the Sun. The tidal force across a 2-meter human body at the ISCO of such an object would be gentle enough that you might not notice it immediately. The enormous physical scale of the black hole means the gradient across your body is mild. For a stellar mass black hole like ours, the calculation is different. At the ISCO, 180 kilometers from the center, the tidal force across a body of typical human height amounts to many thousands of times the surface gravity of Earth. Your body would be experiencing the beginning of violent disruption. The process of being stretched by differential gravity, elongation along the direction of fall, compression perpendicular to it, has its own vivid name in the popular science: spaghettification. It is a word that arrived from informal use and turned out to be technically accurate. Pause here. 3 Schwarzschild radii, the inner edge of the stable disk, time flowing at 81.6% of its distant rate. Tidal forces are beginning to register. The event horizon, 60 kilometers below us, for our specific black hole, is still a full Schwarzschild radius away. We can still, in principle, generate enough thrust to climb back out. We are still, technically, in the region of space where escape remains possible. But the geometry is tightening around us. The photon sphere is only 30 kilometers below. The event horizon is 60. Between here and there, time dilation will cease to be a measurable deviation from normal and become a fundamental feature of the landscape, something that shapes not just clocks, but the entire structure of what future and past mean. The journey inward continues. Picture yourself suspended 75 kilometers from the center of the black hole, in a silence so complete that the only sound reaching your awareness is the rhythm of your own breathing. This is the final approach. The event horizon lies 15 kilometers ahead. You are at approximately 1¼ Schwarzschild radii from the center, still technically outside the point of no return, still in a region of space-time where a future pointing away from the black hole mathematically exists. But that future is growing narrow. The geometry is tightening around it. Take stock of where we are. 75 kilometers from the center. Time on your wristwatch is now running at roughly 45% of its rate at infinity. Every 10 heartbeats you count, a clock hovering in deep space counts 22. The difference is no longer a subtle correction requiring atomic instruments. It is a physical fact that has reshaped your entire relationship with the universe you departed. If a distant observer were tracking your transmitted signals through a sufficiently powerful telescope, they would already see your movements as unmistakably slowed. Not slightly slowed, the way a floor clock runs slow compared to a ceiling clock. Dramatically, visibly slowed. Your hand moving toward your face would appear to take nearly twice as long by their reckoning as by yours. The light carrying images of your body to their instruments is already heavily redshifted. Every photon leaving you is doing work to climb out of this gravity well, expending energy in the climbing, arriving at the distant receiver, shifted toward longer wavelengths, lower frequency, diminished energy. Your transmitted image is growing dimmer and redder with every kilometer you descend. You feel none of this from the inside. Your thoughts are clear. Your perception of passing time is completely normal. The slowing is entirely invisible to you, visible only to the universe you are leaving behind. The sky around you has been transformed beyond ordinary recognition. You have passed through the photon sphere. The entire visible universe, every star in the Milky Way, every galaxy in the observable cosmos, every photon arriving from any direction that is not the black hole, has been compressed by gravitational lensing into a shrinking circle of light in the hemisphere of sky behind and above you. This circle is bright, unnaturally bright, because it concentrates the light of 100 billion galaxies into a single disk. Stars appear multiple times within it, their images bent around the black hole's profile along different paths of curved space-time. The circle is shrinking as you descend, growing tighter, more concentrated. Ahead of you, below you, And surrounding you in a vast hemisphere is the black hole's shadow, Arctur. Darkness so total and so geometrically precise that it seems less like an absence and more like a presence. The sky above has contracted to a pale, luminous disk. The sky above now holds the entire observable universe within a circle perhaps 30 degrees across. The sky above will keep contracting as you fall, drawing the cosmos into an ever tighter point of light, until at the horizon itself, the circle reaches a precise finite angular size that general relativity can calculate exactly. This is not a metaphor for isolation. It is the literal optical consequence of what is happening to the geometry of space-time around you. Light that was distributed over an entire sphere of sky has been redirected by curvature into a cone that grows narrower the deeper you descend. The universe is not receding from you. It is being reshaped by the same geometry that is reshaping time. Your escape velocity at this radius is now climbing above 90% of the speed of light. In the Schwarzschild metric, escape velocity at a radius r is proportional to the square root of the Schwarzschild radius divided by r times the speed of light. At 1¼ Schwarzschild radii, that calculation yields an escape velocity of roughly 89% of light speed. To climb back to infinity from here requires achieving and sustaining a velocity approaching the fundamental cosmic speed limit, and doing so against a continuously strengthening gravitational gradient. The fuel cost is physically impossible for any technology grounded in known physics. You are not formally trapped yet, but you are, in every meaningful sense, committed. The event horizon, in other words, is not where your fate is decided. It is where your fate is formalized. The practical sentence was written earlier, perhaps much earlier, depending on your approach, velocity, and available propulsion. The horizon is the mathematical line in the equations. The point of no return in any engineering sense lies far outside it. Now consider something that complicates the picture further. Almost every real black hole rotates. When a massive star collapses, it carries its angular momentum inward with it. Angular momentum is conserved. A collapsing cloud that was even gently rotating will spin faster as it contracts, the way an ice skater pulls in their arms and spins faster, only compressed by orders of magnitude. The result is a black hole that spins. Roy Kerr's 1963 solution, the Kerr metric, describes the geometry of space-time around such an object, and it introduces an effect without any Newtonian analog: frame dragging. The rotating mass drags the surrounding space-time around with it, the way a ball of viscous fluid spinning in a larger container would gradually set the surrounding fluid in motion. Near a rotating black hole, space-time itself has been set into rotation. Outside the event horizon, but inside a second boundary called the ergosphere, this dragging is so extreme that nothing can remain stationary relative to the distant stars. Even if you fired your engines directly against the rotation, the space-time itself would carry you around. The concept of staying still becomes physically impossible in this region. Not because of any force preventing it, but because the geometry of the space-time has been swept into motion, and you, embedded in that geometry, move with it. The ergosphere touches and merges with the event horizon at the poles of the black hole's rotation axis and bulges outward at the equator. Inside the ergosphere, but outside the horizon, escape remains possible. The ergosphere is not a one-way membrane the way the horizon is. But the energy required to escape from the ergosphere and the trajectory required to do so become increasingly demanding as you descend. For the purposes of time dilation, rotation adds another layer. The rate at which time passes at a given radius around a Kerr black hole depends not just on distance from the center, but on direction relative to the rotation axis, and whether you are traveling with or against the rotation. Counter-rotating orbits experience greater time dilation than co-rotating orbits at the same radius. The geometry of time is no longer a simple radial gradient, but a full three-dimensional field shaped by the rotation. But even setting aside the Kerr geometry, the Schwarzschild solution alone is sufficient to reveal the central phenomenon. And right now, 15 kilometers ahead, the Schwarzschild radius awaits. Something in the geometry is shifting, and it is worth trying to feel it precisely. In flat space-time, time and space are mathematically distinct in a specific sense. You can move freely in any spatial direction, reversing course at will. But you cannot reverse your course through time. The future is one-directional in a way that space is not. This distinction is preserved in ordinary gravitational fields. Near the event horizon, it begins to dissolve in a particular directional way. The equations of general relativity show that as you approach the Schwarzschild radius, the time component and the radial spatial component of the metric tensor exchange roles. What was the radial direction, a spatial direction you could choose to move along or away from, is becoming time-like. It is becoming your future. And what was the time direction, the one-way forward march of moments, is becoming space-like. Reversible in principle, as a spatial direction is reversible. Inside the horizon, the radial direction toward the center is not a place you can choose to travel toward or avoid. It is a temporal direction. The center is in your future the way tomorrow is in your future. Unavoidable. Drawing closer with every moment that passes, regardless of any choice you make. This is the geometry of the interior, and it awaits 15 kilometers ahead. The textbook answer, the version most people carry implicitly when they imagine approaching a black hole, is that crossing the event horizon would be a dramatic, unmistakable experience. The most extreme boundary in the known universe should announce itself. There should be a sensation, a flash, a visible signal that marks the moment of no return. You should feel something. This seems reasonable. The event horizon is, after all, the defining feature of the most extreme objects in physics. It is the threshold beyond which not even light returns, the boundary where time appears, from outside, to freeze entirely. If any location in the universe deserves to announce its presence with physical drama, this is it. But here is what that picture does not account for: the equivalence principle. The equivalence principle is one of the foundational insights of general relativity, and Einstein placed enormous weight on it throughout his development of the theory. It states that the effects of gravity and the effects of acceleration are, locally, within a small enough region of space and over a short enough time, completely indistinguishable. If you are inside a sealed elevator being accelerated upward at the right rate, you feel exactly what you would feel standing on Earth's surface. No local experiment you could perform inside the elevator would distinguish the two situations. Conversely, in free fall, in an elevator whose cable has been cut, you feel weightless. Gravity vanishes locally. Everything in the elevator falls together at the same rate, and from any local measurement, the gravitational field has disappeared. A person falling freely through the event horizon of a sufficiently large black hole is in this situation. They are in free fall. Locally, within the small volume of their own body, over the short duration of the crossing, there is no gravitational field to detect. The tidal forces, which arise from the gradient of gravity across the extent of the body, are present. But for a black hole of sufficient mass, they are gentle at the horizon. For a supermassive black hole like Sagittarius A star, the tidal force at the event horizon across the length of a human body is weaker than what you feel standing on the surface of Earth. You could cross the event horizon of Sagittarius A star and feel in your body nothing more remarkable than ordinary weightlessness. There is no wall at the event horizon. There is no surface. There is no material threshold. There is no flash of light. There is no sudden chill. There is no physical signal of any kind that announces the crossing to the infalling observer. You pass through the event horizon and feel nothing. This is one of the most genuinely strange facts in all of physics. The most absolute boundary in the known universe, the threshold from which not even light returns, passes through you in silence. Hold that in your awareness. Then hold alongside it what the distant observer sees. American physicist David Finkelstein made a key contribution to understanding the horizon in 1958, when he showed that the apparent singularity in Schwarzschild's original equations at the radius, equal to the Schwarzschild radius, was not a physical singularity at all. It was a coordinate singularity, an artifact of the coordinate system Schwarzschild had used, not a reflection of any physical catastrophe in space-time itself. In the Schwarzschild coordinates, which roughly correspond to the time measurements of a distant stationary observer, the metric develops a problematic behavior at the horizon that makes it appear as though time stops there. But by switching to a different coordinate system, one that moves with the infalling observer, the crossing is mathematically smooth and continuous. Physics continues. No law of nature breaks down. The horizon is, in Finkelstein's treatment, a one-way membrane. Light and matter cross it inward without difficulty, but nothing crosses it outward. The crossing is unremarkable from the inside. From the outside, the story is entirely different. A distant observer watching a clock fall toward the event horizon sees it slow progressively. As the clock approaches the horizon, the light it emits must work harder and harder to climb out of the gravity well. Each successive photon carrying information about the clock's position and state arrives at the distant observer redshifted, its frequency lower, its energy diminished. The signals arrive at increasing time intervals because the clock's proper time is running slower than the coordinate time the distant observer uses. As the clock approaches the horizon, its image grows dimmer and redder without limit. From the distant observer's perspective, the clock never crosses the horizon. It approaches, slowing, reddening, fading, and asymptotically freezes at the boundary, its image infinitely dim, infinitely redshifted, preserved forever at the edge. In the mathematics of Schwarzschild coordinates, it takes an infinite amount of coordinate time for the clock to reach the horizon. Not a long time, infinite. The horizon from the outside is infinitely far in the future. The phrase once used for this phenomenon, before Wheeler introduced the term black hole in 1967, was frozen star. Soviet astrophysicists used this term through much of the mid-20th century because it captured exactly what the distant observer sees. A collapsing star frozen at the moment of its event horizon formation, its image preserved at the boundary, growing dimmer over cosmic timescales, but never, in principle, completely gone. The outside universe never witnesses the completion of the collapse. The collapse is perpetually approaching its conclusion without arriving. From the infalling observer's perspective, the crossing happens in finite proper time. They fall through in a perfectly ordinary number of heartbeats, continue into the interior, and find that the universe around them has not dramatically changed in the first moments. The laws of physics continue to operate. Experiments conducted locally give normal results. the crossing is completed. Two accounts, two clocks, two entirely coherent, internally consistent, and mutually irreconcilable descriptions of when the horizon is crossed. Now hold both of these simultaneously, because together they define the strange character of time at the event horizon. For the distant observer, the horizon is a place where the infalling clock's time is infinitely dilated, where proper time, as seen through the lens of coordinate time, has slowed to zero. The clock does not cross. It freezes. From the outside perspective, the horizon represents something close to the absolute maximum of gravitational time dilation, a region where, in the limit, an infinitely long coordinate time passes between any two ticks of the infalling clock. For the infalling observer, none of this is felt. Time continues. The horizon is just a point in space, passed through normally. Both of these are true. The universe contains both descriptions simultaneously without contradiction because the two observers are in fundamentally different regions of space-time, and their descriptions are not directly comparable. They cannot, in principle, compare notes, because the infalling observer, once past the horizon, is in a region of space-time causally disconnected from the outside. No signal the infalling observer sends can ever reach the distant watcher. Their realities are permanently separated. This separation is not a limitation of technology or communication. It is a feature of the space-time geometry itself. Inside the horizon, all future light cones, all the possible paths that light and matter can travel going forward in time, point toward the singularity. No path pointing outward exists. There is no sequence of events inside the horizon that connects causally to any event outside. The interior is not merely remote. It is elsewhere in the structure of space-time, sealed from the exterior by the geometry of future directedness. Here is where the deepest question about black holes, time, and information begins. If no signal can emerge from the interior, what happens to everything that fell in? Every particle that crossed the horizon carried the full specification of its quantum state. Its position, momentum, spin, charge, all of its quantum numbers. General relativity says that information is now inside, causally disconnected from the outside forever. This seems final. The information is gone. But quantum mechanics says something different. A foundational principle of quantum physics, unitarity, demands that information is never destroyed. The complete quantum state of any system can, in principle, be recovered from its future evolution. Not practically. In most cases, the information is scrambled beyond any useful recovery. But in principle, the information must survive. If you burn a book, the information in it is encoded in the smoke, ash, photons, and heat of the burning, scrambled but present in the correlations between particles. The information is not destroyed, merely redistributed. A black hole that simply swallowed information and destroyed it would violate this principle. And yet the geometry of the event horizon appears to do exactly that. In 1974, Stephen Hawking showed that black holes are not perfectly black. A calculation combining general relativity with quantum field theory, the physics of quantum processes in curved spacetime, predicted that a black hole emits a faint, steady radiation from just outside the event horizon. The radiation arises from quantum field effects in curved spacetime near the event horizon. A common visualization describes virtual particle pairs separating near the horizon, though the actual physics is more accurately described through quantum field theory on a curved spacetime background. The escaping partner carries real energy, radiated as heat. This is Hawking radiation, For a stellar mass black hole, the temperature of this radiation is extraordinarily low, a few billionths of a degree above absolute zero for the 20 solar mass black hole we have been imagining, and around 60 billionths of a degree for a 1 solar mass object. Detecting it against the cosmic microwave background radiation that fills the universe is currently impossible. But the principle is what matters. A black hole radiates over an incomprehensibly long span of time, far longer than the current age of the universe for any black hole that has formed from stellar collapse. The radiation causes the black hole to lose mass, shrink, and eventually evaporate completely. The radiation that escapes appears to be purely thermal, random, carrying no information about what fell in. If the evaporation is complete, the black hole leaves behind only this featureless thermal glow, and all the information about every particle that ever fell in appears to have vanished. This is the black hole information paradox, and it has occupied some of the sharpest minds in theoretical physics for 50 years. 2 years before Hawking's radiation paper in 1972, Israeli-American physicist Jacob Bekenstein demonstrated that black holes possess entropy, the thermodynamic quantity measuring the number of microscopic configurations consistent with a given macroscopic state. Bekenstein showed that this entropy is proportional not to the volume of the black hole's interior, as standard thermodynamics would suggest, but to the area of the event horizon. This was a startling result. The information content of a black hole was encoded on its 2-dimensional surface, not in its 3-dimensional interior. Everything that had fallen in, every particle, every quantum state, every bit of information, might be stored somehow on the horizon itself, not lost in the depths below, written on the boundary. Bekenstein's area-entropy relationship seeded a profound conjecture that the entire physical content of a region of space might, in principle, be fully described by information encoded on a lower dimensional surface bounding that region. This is called the holographic principle, and while it remains speculative as a claim about the universe at large, it has been given rigorous mathematical form in specific frameworks. The most developed is the ADS/CFT correspondence, published by the Argentine theoretical physicist Juan Maldacena in late 1997, which demonstrates a precise duality between a theory of gravity in a certain kind of higher dimensional space and a quantum field theory without gravity on the lower dimensional boundary of that space. In this framework, nothing is lost. The information content of the interior is fully encoded on the boundary and, in principle, recoverable from the Hawking radiation. Some researchers believe this resolution is correct. Information survives, encoded in subtle correlations between Hawking radiation particles that appear random individually, but contain in their correlations the full quantum state of everything that fell in. Others believe something more radical is required. In 2012, physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully proposed that resolving the information paradox without violating quantum mechanics requires the event horizon to be not the smooth, unremarkable threshold that the equivalence principle implies, but a region of intense high-energy radiation, a firewall that would destroy any infalling observer at the moment of crossing. If the firewall hypothesis is correct, the equivalence principle is violated at the horizon. The infalling observer's smooth experience of crossing is an illusion, and the gentle silence of the threshold is replaced by annihilation. The debate between these positions, holographic resolution versus firewall, smooth crossing versus incineration at the boundary, has not been resolved. What both positions agree on is that something genuinely new in physics is needed at the junction of general relativity and quantum mechanics, and that the event horizon is precisely where that need becomes most acute. Take stock of where we are. We have crossed the photon sphere. We have descended past the innermost stable orbit. We have arrived at the event horizon and understood it from two irreconcilable perspectives: the silence the infalling observer feels, and the eternal freeze the distant observer sees. We have encountered the information paradox and recognized it for what it is. Not merely a puzzle about black holes, but a deep incompatibility between the two most successful theories in physics, surfacing at the place where time dilation becomes maximal. Inside the horizon, the future does not point outward. The future points toward the center, toward the singularity or whatever occupies that position if quantum gravity intercedes before infinite density is reached. Time inside a black hole has not stopped. It has been geometrically redirected. The radial direction inward is now your future, as unavoidable as tomorrow is on the outside. We are going in. Stand inside this geometry for a moment, as much as language can place you there. You have crossed the event horizon. The crossing itself was unremarkable. No sensation, no flash, no physical announcement. One moment you were outside. Now you are inside. The difference exists entirely in the geometry of space-time, in the structure of which direction your future points, and not in any local, immediate, feelable property of the space around you. But the geometry has changed in ways that deserve careful attention, because what it means for time here is unlike anything we encountered on the approach. The intuitive picture of the black hole interior is straightforward enough. Extreme gravity pulls you toward a central point, the singularity, which sits at the center of the black hole, the way the core of the Earth sits at the center of our planet. You are falling toward a place, an extreme place, a lethal place, but a place located at the bottom of the gravity well, accessible if you travel in the right direction, avoidable in principle if you had some means of counteracting the pull. That picture is wrong in a way that changes everything. The singularity is not below you. The singularity is ahead of you in time. In the Schwarzschild solution, the mathematical description of space-time around a spherical, non-rotating mass, the coordinate r(k) describes the radial distance from the center. Outside the event horizon, r is a spatial coordinate. It tells you where you are in space, and you can choose to increase it, move outward, or decrease it, move inward as you please. The coordinate t, meanwhile, behaves as a time coordinate in the ordinary sense. It flows forward, it measures the progression of moments. It is the direction you cannot reverse. At the event horizon, these roles begin to exchange. Inside the horizon, in the Schwarzschild geometry, the r coordinate becomes time-like. The t coordinate becomes space-like. This is not a mathematical trick or a coordinate artifact. It is a genuine physical change in the structure of space-time. Inside the horizon, decreasing r is not a spatial direction you can choose to travel toward or away from. It is the future. It is as mandatory, as irreversible, as unavoidable as the forward passage of time on the outside. Every path you could take through the interior leads towards smaller r. Every trajectory, no matter what direction through the spatial dimensions you move, no matter what you do with a rocket engine, every possible future path in the interior decreases r. The singularity at r equals 0 is not a place you fall toward. It is a moment you are moving toward, the way all of us are constantly moving toward tomorrow. You cannot avoid the singularity inside a black hole for the same reason you cannot avoid next Tuesday. not because of the strength of some force acting on you, because of the shape of time. The outside universe is still visible above you, through the circular opening that the event horizon represents from the inside, a bright ring of compressed, blue-shifted light. You can still see the stars and galaxies you came from. The ring is distorted, concentrating the light of the entire exterior cosmos into a single luminous circle that appears to diminish as you fall. The universe you came from is still there, still emitting light, still running at its faster coordinate time. But the light you receive from it carries older and older information as you descend. You are seeing the universe as it was at progressively earlier moments before your crossing. Ahead, in the direction that is now your future, is darkness. Not the darkness of empty space, where at least some starlight eventually arrives. The darkness of a future that cannot send you light before you arrive in it. The singularity does not illuminate itself. Your body, in the final moments inside a stellar mass black hole, is experiencing tidal forces that have grown far beyond survival. For our 20 solar mass black hole, the tidal disruption began before the horizon crossing and has continued to intensify. The differential in gravity between your head and your feet, the gradient that stretches you in one direction and compresses you in the perpendicular, has reached values that no biological or mechanical structure could withstand. The process is not painful in any human sense, because pain requires a functioning nervous system, and the tidal disruption has exceeded that threshold well before this point. For a supermassive black hole, the situation is gentler. The tidal forces at the horizon of Sagittarius A star are mild enough that biological survival through the crossing is conceivable in principle. Inside, the forces increase steadily. The maximum proper time available between the event horizon and the singularity of Sagittarius A star, with its 4 million solar masses and Schwarzschild radius of 12 million kilometers, is perhaps tens of seconds to a few minutes for an infalling observer. Not long, but long enough, in principle, to be conscious. Long enough to observe the distorted universe through the shrinking ring above. For our stellar mass black hole, the maximum proper time from horizon to singularity is measured in microseconds. These microseconds are the entire interior experience. There is a remarkable feature of interior geodesics worth understanding before we proceed. An infalling observer who wants to maximize their proper time before reaching the singularity should do nothing. No thrust, no acceleration, no deviation from free fall. The maximum proper time interior traversal is the passive, unpowered geodesic. Firing a rocket toward the singularity arrives sooner. Firing a rocket away from the singularity, attempting to prolong the experience, to stay away from the future, also arrives sooner. Any deviation from free fall shortens the remaining time. The geometry is such that resistance is not merely futile, it is counterproductive. The most time you get is given freely to the traveler who surrenders entirely to the geometry. Every path leads towards smaller r. Every trajectory bends toward the same future. Every second of proper time is a second closer to the place where the equations of general relativity stop making finite predictions. The proper time runs out, the singularity is reached. Now consider what that means. We have traveled from the wristwatch on your arm, where time runs at the specific local rate of Earth's gravitational field, through the photon sphere, the innermost stable orbit, the event horizon, and into the interior. At each stage, the time dilation factor has grown, from negligible at large distances to 57% at the photon sphere, to 45% at the final approach, to effectively zero from the outside perspective at the horizon, to something that no longer applies in the same way on the inside, where the very concept of time has been geometrically redirected. We have followed time dilation to its extreme conclusion, and that conclusion is not a clock ticking at zero. It is a clock that has passed through a threshold where the time axis and the space axis exchanged roles. The extreme of time dilation is not timelessness. It is transformation. Every physical theory has an edge, a place where its equations cease to produce meaningful predictions and begin to generate infinities or contradictions that signal the theory's limits. In Newtonian gravity, the edge appears when speeds approach light. In special relativity, the edge appears when curvature is included. In general relativity, which handles both of those regimes with precision, the edge is the singularity. At the singularity, the equations of general relativity predict that space-time curvature diverges to infinity. Mass density diverges to infinity. The tidal force across any finite-sized object diverges to infinity. These infinities are not a description of a physical reality. They are the signature of a theory operating outside its range of validity. The same kind of infinite that appeared in early calculations of blackbody radiation before quantum mechanics was understood, or in certain calculations in electrodynamics before renormalization was developed. The singularity is where general relativity fails, not necessarily where the universe fails. At scales approaching the Planck length, approximately 1.6 times 10 to the power of -35 meters, the scale at which quantum gravitational effects should become comparable to classical gravitational effects. The smooth, continuous geometry that general relativity assumes almost certainly gives way to something else. A theory of quantum gravity, combining the principles of general relativity with those of quantum mechanics, should describe this regime and produce finite, physically sensible predictions where general relativity generates infinities. The problem is that no complete theory of quantum gravity yet exists. Loop quantum gravity, one serious candidate, constructs space-time from discrete fundamental units, tiny quanta of geometry, each roughly a Planck volume in size. In this framework, space-time has a granular structure at the smallest scales, like the way a photograph appears smooth at normal viewing distances but resolves into pixels under magnification. In loop quantum cosmology, the application of loop quantum gravity to the early universe, the Big Bang singularity is replaced by a quantum bounce, a moment of maximum density from which the universe rebounds rather than collapsing to a mathematical point. Some researchers have extended this reasoning to black hole interiors, proposing that the classical singularity is replaced by a quantum bounce, and that the interior of a black hole might connect through this bounce to an expanding space-time region. Whether this region is accessible to any observer, or whether it is a separate space-time that has no future interaction with the black hole's original space-time, is not yet clear. String theory approaches the problem differently. In string theory, the fundamental entities of physics are not point particles, but tiny extended strings whose vibrational modes correspond to the different particles of the standard model. Point particles can produce true mathematical infinities when they interact at zero separation. Extended strings cannot. The fundamental scale of the string provides a natural cutoff that smooths the infinities. Near the Planck scale at the singularity, stringy effects are expected to modify the geometry and potentially replace the infinite curvature of the classical singularity with something finite and traversable. How this plays out precisely inside a black hole interior is a subject of ongoing research. Both of these frameworks share a common admission. They are incomplete. They generate interesting predictions, some mathematically rigorous within their own formalisms, but neither has been experimentally confirmed, and neither can yet describe the full physics of the interior of a black hole. We do not know what happens at the singularity, not because the question hasn't been asked with sufficient seriousness, not because the mathematics hasn't been pushed hard enough. We do not know because the regime is beyond the range of any theory we currently possess, and because the singularity's interior is structurally separated from all observational access outside the horizon. Whatever happens there, quantum bounce, string smoothing, something entirely unforeseen, is behind a geometric curtain that no signal can penetrate. Some researchers believe the singularity is physically real, an endpoint in time where the curvature of space-time becomes as extreme as it can be, and where the universe inside the horizon literally ends. Others believe the singularity is an artifact of using classical general relativity beyond its range of validity, and that quantum gravity will replace it with something finite, a maximum density, a bounce, a transition to a new space-time. The evidence that would distinguish these views is inaccessible by construction, sealed inside the event horizon. Not a matter of current technological limitation, a matter of the geometry of space-time itself. The singularity is the place where the map runs out, not the edge of the known universe, the edge of the knowable universe for all observers outside the horizon. Now pull back, step away from the singularity, from the interior, from the event horizon, and look at everything we have covered. We began on the surface of the Earth, where time runs at a specific rate determined by Earth's mass and your altitude in its gravitational field. We established that this rate is real, measurable, and different from the rate at which time runs in free space, confirmed by Robert Pound and Glenn Repka in 1959, confirmed daily by GPS satellites, confirmed to extraordinary precision by atomic clocks at different altitudes. We then traveled outward toward a stellar mass black hole and documented the systematic deepening of gravitational time dilation as we descended. Mild at large distances, significant at the photon sphere, dramatic at the final approach, infinite from the outside at the event horizon, transformed into something else entirely inside. What this journey has forced into view is something the question we started with, why does time stop near a black hole, was already assumed without examination. Time is not uniform. Time is not universal. Time is not the skeleton of the universe that Newton described, the fixed, equable flowing backdrop against which everything else happens. Time is a dimension of space-time that curves with mass. It runs differently depending on where you are and how you are moving. It can be stretched to any degree. It can be geometrically transformed inside the horizon, from a temporal direction into a spatial one and back again. It can appear to stop entirely from one perspective while continuing normally from another. It can reach a terminus at the singularity that may or may not be a genuine physical endpoint, depending on which theory of quantum gravity eventually proves correct. But there is something deeper still that the black holes is showing us. Something that the entire journey from your wristwatch to the event horizon and beyond was pointing toward in every section, at every scale. Time is always relational. It is always measured from somewhere, by something, relative to some reference frame. There is no view from nowhere. There is no cosmic clock against which all other clocks are measured and found to be running slow or fast. Newton's absolute time, the equably flowing river, does not exist. What exists in its place is a web of local times, each valid within its frame, each in principle translatable to any other frame by the rules of general relativity, but none more fundamental than any other. The clock on your wrist and the clock at infinity are both keeping real time. They are keeping different times. Both are correct. Near a black hole, this relativity of time is pushed to an extreme that cannot be explained away or minimized. The outside observer's time and the infalling observer's time diverge without limit at the event horizon. No shared now exists between them. No fact about when the horizon was crossed is observer independent. And this is where the quiet question at the heart of everything surfaces. What is time? Not what does time do? Not how does time behave in curved space-time? Not how is time measured by different observers? But what is it? Is time the thing that ticks on your wristwatch? The steady forward pulse of a cesium atom cycling between energy states? Is it the coordinate that a distant observer assigns to events? The bookkeeping device that lets them label which came first and which came second in the history of the universe they can see? Is it the proper duration experienced along a specific world line? The time you live through? The time your cells age by? The time your memories accumulate in? Is it the geometric structure of the space-time manifold that gives events a causal order, that distinguishes your past light cone from your future light cone and seals the two from each other? Is it something that emerges from the second law of thermodynamics, not a feature of the equations, which are mostly time-symmetric, but a consequence of the fact that the universe began in a state of extraordinarily low entropy and has been increasing ever since, giving macroscopic time its one-way arrow, while the microscopic laws remain perfectly reversible in both directions? Is time fundamental, built into the bedrock of reality, prior to any physical process, the stage on which everything else performs? Or is it emergent, arising from something deeper, from the structure of quantum entanglement between subsystems of the universe, from the correlations that build up between interacting quantum systems, from the thermodynamic arrow that makes one direction through the configuration space of the universe look like the past and the other look like the future? Some researchers in quantum gravity now argue that time itself may not appear in the most fundamental equations. The Wheeler-DeWitt equation, a key equation in canonical quantum gravity, derived in the 1960s by physicist John Wheeler and independently by Bryce DeWitt, contains no time variable at all. It describes the quantum state of the universe without any reference to a time coordinate. Time, in this framework, may be something that emerges for observers embedded within the universe, from the relational structure of their interactions with the rest of the quantum state, rather than something that the universe as a whole possesses. The universe itself, viewed from outside, if such a view were possible, might have no time at all. Only observers inside the universe, correlating their states with the states of other subsystems, experience the forward flow. What happens to emergent time near a black hole, where the space-time geometry becomes extreme? What happens to it at the singularity, where the smooth geometry of general relativity breaks down and is replaced, presumably, by discrete quantum structure? What happens to it at the Planck scale, where space and time themselves may dissolve into a foam of quantum fluctuations? A regime so remote from everyday experience that no analogy from macroscopic physics reliably applies. Can we know what happens at the singularity? Not in the present state of physics, not with the current theoretical framework, not while the event horizon seals the interior from any external observation. The singularity is structurally unknowable from outside, in a precise and irreducible sense. Not a gap in our knowledge that better instruments will close, but a consequence of the space-time geometry that no advance in technology can circumvent. This is not merely what we do not yet know. This is what we cannot know, not because of ignorance, but because the physics of the event horizon forbids the information from reaching us. What remains on the outside of the horizon is the implication, the lesson, the reframing that the black hole has forced. Time does not stop near a black hole. That framing, the one we started with, turns out to be built on a premise that the physics has gently and thoroughly dismantled. Time appears to stop from the outside for an infalling object at the event horizon. From the infalling object's own perspective, time continues without interruption. Both descriptions are complete. Both are valid. Neither is more fundamental. The appearance of stopping is real. It is not a trick of light delay or perceptual limitation. But it is a feature of one observer's description, not of time itself. What the black hole reveals is that time was never the absolute river. It was always this, curved, relational, local, perspectival, emergent from the specific geometry of the specific path through the specific gravitational field. The black hole does not create this relativity of time. The black hole makes it inescapable. It turns the dial up until the two descriptions, outside observer and infalling observer, diverge by an infinite factor, and there is no way to pretend any longer that a universal time underlies them both. Newton's absolute time does not exist. What exists is an infinite collection of local times, each real, each valid, each measuring a genuine physical quantity, and none of them measuring the same thing as any other, once gravity is strong enough to make the difference impossible to ignore. The black hole, in the end, is not a destroyer of time. It is a revealer of what time has always been. Step outside for a moment, if you can. Or close your eyes and picture it. A clear night, the air cool against your face, the stars overhead vast and still. The room you were in, with all its warmth and familiarity, is behind you. Ahead is the sky. The same sky that has hung over every human who has ever looked up and wondered about what time is and where it goes. Look at your wristwatch. It is still there on your arm, ticking, advancing 1 second at a time with the steady, mechanical patience it has always shown. It has been ticking since you began this journey. It kept time through Newton's absolute river, through Einstein's curved space-time, through the photon sphere and the innermost stable orbit and the event horizon and the geometry of the interior. It did not slow from your perspective. It did not falter. It kept its honest, local, specific record of time passing in this gravitational field, at this altitude, on this path through the universe. That watch is different now, not because it has changed, because you have understood what it is. The journey we have taken, from your wrist to the Schwarzschild radius and through, is complete in outline. The technical architecture has been laid down. Mathematics has done its work. What remains in this quieter space is not more calculation, but something harder to name. The sitting with it. The allowing of what we have found to settle into the body and the bones. So stay here for a moment, under the stars, with the watch on your arm. Consider what the night sky is actually showing you, now that you know what you know. Every star you can see is generating its own gravitational field. Every star is curving the space-time around it, creating its own local time gradient, ticking at its own rate relative to a clock in deep, empty space. The sun, 93 million miles from where you stand, causes time to run slower at its surface than it does here, and slower still at the surface than it does at the Earth's own surface, because the sun is more massive. The red giants and white dwarfs scattered across the sky each have their own relationship with the time around them. The pulsars, The rapidly spinning neutron stars whose electromagnetic pulses sweep the galaxy like lighthouse beams are keeping their own proper time in a gravitational field tens of thousands of times stronger than Earth's. Every one of these objects is a different clock. Every one is correct. None of them agree with each other in absolute terms, and none of them is keeping the wrong time. Every star above you is keeping its own local time. Every atom in every stellar core is cycling through nuclear reactions in a time that differs from yours by the depth of the gravity well it inhabits. Every photon crossing the void between distant galaxies and your retina carries information from a moment that has, by the time of its arrival here, become the past. Not merely the past in the sense of travel time, but the past in the precise relativistic sense that the moment of emission and the moment of reception are separated by a space-time interval that no force and no technology can reduce to zero. You are looking at a sky that is not a single now. You are looking at a composite of countless local times smeared across billions of years of proper time in different gravitational fields, arriving at your eyes simultaneously from radically different temporal depths. The star you see as a small blue point in the constellation. Orion is not there right now in any shared sense. The concept of right now applies only here for you in this gravitational field, on this path. Everywhere else in the universe has its own right now, and none of them are the same as yours. This is not a cause for disorientation. It is a cause for something quieter and more precise. You are located. You are specific. You are a clock keeping honest time in a specific corner of the universe, in a specific gravitational field, on a specific path through space-time. This is not a limitation. This is your condition, and it is the condition of everything that exists. Somewhere in the direction of the constellation Sagittarius, 26,000 light-years away at the center of the galaxy. Sagittarius A star is curving space-time around its 4 million solar masses at this very moment. Its event horizon, 12 million kilometers across, is bending time in the way we have spent this entire journey exploring. The accretion disk around it, if material is currently present, is radiating at temperatures of millions of degrees, emitting X-rays that will cross the galaxy and arrive here tens of thousands of years from now. The black hole is doing what black holes do, in its local time, in its local geometry, in complete indifference to the fact that we have been discussing it. And above you, at this moment, GPS satellites are doing something remarkable. They are correcting their clocks silently, automatically, 60 times a day, to account for the fact that their local time differs from your local time. Their clocks run fast because they are in weaker gravity. They run slow because they are moving at orbital velocity. The net correction, applied continuously by software built on Einstein's equations, keeps the clocks in the satellites synchronized with the clocks on the ground, so that when you ask for directions, the position calculated from the travel time of radio signals is accurate to a few meters, rather than accumulating errors of kilometers per day. The physics that governs time near a black hole and the physics that governs GPS satellite clock corrections are the same physics, operating at vastly different scales, producing effects that range from the barely detectable to the causally infinite. There is something deeply restful in this, once the technical scaffolding settles into the background. Your proper time is real. The seconds accumulating on your wristwatch are real. The duration of your life, counted in heartbeats and breaths and the slow accretion of days, is a genuine measurement of something genuine. It is not diminished by the fact that a clock on the other side of the galaxy is ticking at a different rate. It is not made uncertain by the fact that a clock near the event horizon of Sagittarius A star is running at a fraction of your rate. These are not competitors. They are all correct. They are all local. They are all keeping honest time in their specific circumstances. The river of time was always a stream, bounded, local, specific. The discovery that it was never a river was not a loss. It was an act of honesty. The stream is real. The stream is yours. Rest here for a moment. Take a breath. The machinery of the technical explanation has done what it could. What follows requires a different kind of attention. This question, why does time stop near a black hole, has been with humanity in various forms for longer than the physics to answer it has existed. The question beneath the question, the one that has driven every physicist and philosopher who has wrestled with the nature of time, is still older. It is as old as the human capacity for wonder and as persistent as any question we have ever asked. What is time? In the 4th century before the Common Era, Aristotle addressed the question with the careful, systematic attention he brought to everything. Time, he concluded in his Physics, was the measure of motion with respect to before and after. It was not a thing in itself, not a substance, not a place, but a relational property of moving objects. Without change, there could be no time. Without a mind capable of perceiving and counting the before and the after, time, Aristotle suggested, might not exist at all. The question of whether time requires a perceiving mind was planted in the philosophical tradition by Aristotle and has never been fully answered since. 7 centuries later, Augustine of Hippo returned to the question with an urgency that Aristotle's systematic calm had not conveyed. Writing in his Confessions around 400 of the Common Era, Augustine arrived at one of the most honestly vulnerable passages in the history of philosophy. What, then, is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. He proceeded to develop a conception of time as interior, as existing in the mind rather than in the external world. The past exists as memory, he argued. The future exists as an expectation. The present exists as attention. And all three forms, what he called the present of past things, the present of present things, and the present of future things, exist in the soul, not outside it. Time, for Augustine, was the distension of the mind across its own experience. This was not scientific. It was not mathematically formalized. But it captured something that physics has continued to circle back toward, the intimate relationship between time and the observer embedded within it. Isaac Newton, in 1687, gave the Western world the answer it had been waiting for. Precise, external, absolute. Time flowed equably, independent of everything, the same everywhere, the permanent skeleton of the universe. 200 years of extraordinary scientific productivity confirmed the framework within every precision available. Newton's absolute time was not wrong within its domain. It was simply incomplete. Immanuel Kant, in his Critique of Pure Reason, published in 1781, offered a different resolution. Time was neither a feature of the external world, as Newton had claimed, nor merely a feature of the internal mind, as Augustine had suggested. It was a form of intuition, a structure imposed by the human mind on all experience prior to any particular perception, making experience possible in the first place. Without the form of time, nothing could be experienced as having a before and after, a cause and effect, a past and future. Time was real for Kant, but its reality was inseparable from the structure of the experiencing mind. It was not the world that had time. It was the subject, encountering the world that organized the encounter temporally. Kant was writing before the physics of relativity existed, and he could not have anticipated what Einstein would show. But his insight that time is bound to the observer is not entirely wrong in the light of what relativity has revealed. The relativity of simultaneity, the fact that two spatially separated events that are simultaneous for one observer are not simultaneous for another, with neither observer being more correct, has a Kantian flavor. Time, in relativity, is not the world's clock. It is the relationship between events as experienced from a specific frame. In the spring of 1922, at a meeting of the French Philosophical Society in Paris, two of the 20th century's most formidable intellects met to discuss the nature of time directly. Albert Einstein and the French philosopher Henri Bergson engaged in an exchange that was polite in tone and irreconcilable in conclusion. Bergson had spent decades developing a philosophy of time centered on the concept of durée, lived duration, which he distinguished sharply from the mathematical time of physics. For Bergson, who published his first major work on time in 1889, the measurable, divisible, spatialized time of physics was an abstraction from the genuine temporal experience of conscious beings. Lived time flowed continuously, with texture and depth, inseparable from memory and anticipation. The multiple times of Einstein's relativity were measurements, Bergson argued, abstractions useful for physics, but not descriptions of the time that beings actually inhabit. Einstein's response was clear. There was, for him, a single time, the time of physics, measurable, relative, and real. A philosopher's time that differed from the physicist's time was, in Einstein's view, not a different kind of time, but a different kind of subject matter. The physicist measured what could be measured. What could not be measured was, for physics, not time. The debate was not resolved then, and it has not been resolved since. What both men were touching, from different directions with different tools, was the same deep question. Is time something the universe has, or something observers within it have? And what happens to the answer when the observer is pushed to extremes? The black hole is the most extreme answer to that question the universe provides. British physicist Julian Barber, in his 1999 work, The End of Time, carried the argument further than Bergson or Einstein had taken it. Barber argued on the basis of the Wheeler-DeWitt equation and the formalism of canonical quantum gravity that time does not appear in the most fundamental description of the universe. The Wheeler-DeWitt equation, derived in the 1960s by John Wheeler and Bryce DeWitt in an attempt to quantize general relativity, describes the quantum state of the entire universe without a time variable. In this framework, the universe is a static object, a superposition of all possible three-dimensional geometrical configurations, each associated with a quantum amplitude, but none embedded in a flowing time. The experience of time, Barber argued, emerges from within this static structure, from the fact that certain configurations contain records, memories, structures that correlate with other configurations in ways that feel, to observers embedded within them, like a sequence. Time, in Barber's picture, is the story that correlated quantum states tell each other about their relationships. Whether Barber is right remains genuinely open. Other physicists and philosophers have argued that time is fundamental, that the timelessness of the Wheeler-DeWitt equation reflects a technical feature of the mathematical formalism, rather than a physical fact about the universe, and that dismissing time as emergent creates more problems than it resolves. Some researchers think time is a fundamental feature of reality, that the correct mathematical formulation will eventually reveal. Others think time is genuinely emergent, arising from quantum correlations between subsystems, and that no time variable will appear in the final theory. The debate is alive precisely because the evidence, the interior of black holes, the physics of the Planck scale, the full theory of quantum gravity, is not yet available. But the arc of the debate, from Aristotle's time as measure of motion, through Augustine's interior duration, Newton's absolute river, Kant's form of intuition, Bergson's lived durée, Einstein's relative coordinate, and Barber's emergent correlation, is the arc of our species slowly, carefully, honestly abandoning the certainty that time is simple. It was not absolute. It was never absolute. It was always local, always relational, always the specific measurement of the specific curvature of the specific path. The black hole did not invent this truth. It revealed it with a violence and a clarity that nothing else in the observable universe can match. From far away, the black hole deepens time gently. At the photon sphere, it dilates time measurably. At the event horizon, it freezes time for the outside observer while allowing it to continue for the infalling one. Inside, it transforms time into a direction through space. At the singularity, if such a thing truly exists, it appears to end time entirely, or at least to exhaust the theory that describes it. This is the universe's most extreme statement about what time is, and the statement is, time is not the absolute river. Time is the local, honest, specific curvature of the path you are on. Look at the wristwatch on your arm again. It is not keeping an approximate time. It is not keeping parochially inconvenient time that differs from some deeper cosmic standard. It is keeping the only kind of time that exists, the time of this place, this gravitational field, this path through space-time. Its every tick is a measurement of the curvature of the Earth's gravitational field at this altitude. Every second is a second of genuine proper time along the world line of this planet, this body, this life. There is a melancholy in what the black hole has shown us. Some truths arrive with weight. We cannot know what the singularity is. The physics required to describe it does not exist in a complete form. The interior of the black hole is sealed by the event horizon from all observation by anyone outside. And this sealing is not a temporary limitation of technology, but a permanent feature of the causal structure of space-time. The things that fell into the black hole over its lifetime, the gas and dust and light, the information carried by every quantum state that ever crossed the horizon, may survive encoded in Hawking radiation in principle, but recovering that information would require capabilities no finite observer within the universe can possess. The universe has drawn a boundary and said, beyond this point, you cannot know. Not because you have not tried, because the geometry does not permit it. There is something to grieve in that, if grief is the right word. The acknowledgement that some questions are not merely unanswered, but structurally unanswerable. That the universe contains regions of itself that it has placed permanently beyond our reach, is a kind of limit that the human drive toward understanding does not accept comfortably. And yet, the boundary itself is a form of knowledge, knowing precisely where the limit of knowability lies, knowing that the event horizon is a causal horizon, not a physical wall, knowing that the freeze seen from outside and the smooth crossing experienced from inside are both correct, and neither is more fundamental, is itself a profound understanding of the universe's structure. Newton did not know where the boundary was. He did not know there was one. Einstein found it and described it with equations precise enough to predict the geometry of space-time around an object not yet observed, in a universe far stranger than anyone before him had imagined. The knowledge that we cannot know certain things is not a failure of knowing. It is the map extended to its honest edge. The wristwatch on your arm, ticking forward in the specific time of this specific planet, this specific gravity well, is real and complete. Every second it marks is a second of genuine existence. The relativity of time, the fact that a clock near the event horizon of Sagittarius A star is ticking at a tiny fraction of this watch's rate, the fact that a clock aboard a GPS satellite is ticking slightly faster, does not diminish any of these times. It confirms them. Each is local. Each is honest. Each is the exact and appropriate measure of the curvature of space-time at its location. Time does not stop near a black hole. Time reveals itself near a black hole. It reveals that it was always curved, always local, always relational, always bound to the mass surrounding it, and the path through space-time of whatever is measuring it. The stopping, the infinite time dilation at the event horizon from the outside perspective, is the full expression of a truth that was always present in a much milder form in the 22 meters of the Harvard Tower, where Pound and Rebka worked in 1959, and in the sub-millimeter height differences that modern atomic clocks can now detect, and in the GPS corrections that keep your navigation accurate, and in the slight difference between the clock at the floor of this room and the clock at its ceiling. The black hole is not a place where time ends. It is the place where time can finally be seen whole. Not as the absolute river that Newton described, not as the mysterious interiority that Augustine felt, not as the form of intuition that Kant imposed, not as the lived duration that Bergson defended, but as the geometry of the path, specific and local and honest, belonging to whoever travels it. The wristwatch on your arm has been ticking for the entire duration of this journey. It did not pause while we traveled from the surface of the Earth toward the edge of a stellar mass black hole. It did not falter while we examined the interior geometry where time and space exchange roles. It kept its honest, local, specific record of the passage of proper time in this gravitational field, on this path, through all of it. That is the whole story, in miniature. That is where we began, and it is where we return. Newton told us the watch was keeping universal time, the same time that ticked at every point in the cosmos, independent of everything, the fixed backbone of the universe. For 200 years, the evidence supported this picture well enough to build civilizations on. The watch on your arm, the clock in a distant observatory, the imagined timepiece at the edge of the observable universe, were all, in Newton's framework, ticking in perfect unison, marking the same moment, keeping the same second. Time was absolute. Time flowed equably. Time was the skeleton of reality, and nothing that happened inside the universe could alter its rate. Then Einstein showed otherwise, in 1905, before he had even developed his full theory of gravity. Time, he demonstrated, was elastic with velocity. A clock on a fast-moving spacecraft ticks slower than a stationary one, not because the spacecraft clock is defective, but because time itself dilates with motion. The stretching is real. The astronaut who returns younger is genuinely, biologically younger. The twins have aged differently. The river has different currents in different channels, and the channels cannot be reunited into one. Then came 1915 and the far stranger revelation. Gravity curves not only space, but time. The deeper you sit in a gravitational well, the slower your clock runs relative to a clock hovering in weaker gravity. Robert Pound and Glenn Rebka confirmed this in 1959 to 1960 in a 22.6-meter tower at Harvard University, measuring the precise redshift of gamma rays climbing from the basement to the top floor and finding agreement with Einstein's prediction to within about 10%. A result later refined to within 1% by Pound and Snyder in 1964. 22 meters. The floor and the ceiling are not at the same time. Every GPS satellite in orbit corrects for this effect 60 times a day, accounting for the fact that its clock, in weaker gravity at higher altitude, runs fast relative to the clocks on the ground it serves, and that without the correction, positional errors would accumulate at roughly 11 kilometers per day. The physics of time dilation is not an abstraction confined to extreme environments. It is engineered into the devices in your pocket. From that foundation, we began to travel. We established what a black hole is, a region of space-time where the escape velocity exceeds the speed of light, bounded by the event horizon. The Schwarzschild radius, derived by Carl Schwarzschild in 1916 while stationed at the Russian front, sent to Einstein from a battlefield, published before its author died. Subrahmanyan Chandrasekhar calculated in 1931 the mass limit beyond which no electron pressure can halt collapse. Roger Penrose proved in 1965 that singularities are not exotic possibilities, but the mathematical consequence of sufficient gravitational collapse. John Wheeler named the object in 1967, giving language to the absence. We traveled toward a stellar mass black hole and watched the time dilation deepen at each radius. At the photon sphere, 1.5 Schwarzschild radii from the center. Clocks tick at 57.7% of the rate at infinity, and the entire visible universe has been compressed by gravitational lensing into a shrinking circle of light overhead. Arthur Eddington's 1919 light-bending confirmation, writ incomprehensibly large. At the innermost stable circular orbit, 3 Schwarzschild radii, clocks run at 81.6% of the rate at infinity, and this is the glowing inner edge of the accretion disk, the annulus of heated plasma that can outshine entire galaxies. When Roy Kerr's 1963 rotating black hole geometry allows efficiency approaching 42% of rest mass energy, more than 8 times what nuclear fusion in stellar cores can manage, the engine of quasars, the brightest sustained objects in the observable universe. Closer still, and the final approach reduced the escape velocity to a fraction from the speed of light, compressed the universe above into a pale, contracting disk, slowed the transmitted clock to 45% of the distant reference rate. Every photon climbing outward from this depth was redshifted by the work of the climb. Every signal arriving at the distant observer stretched and dimmed by the depth of the gravitational well it had to traverse. And then the event horizon. David Finkelstein showed in 1958 that the apparent singularity in Schwarzschild's original coordinates at the horizon was a coordinate artifact, a limitation of the mathematical description, not a physical catastrophe in spacetime. An infalling observer, guided by the equivalence principle, crosses the horizon in free fall, feels nothing unusual, and continues into the interior. The horizon passes through them in silence. From outside, the infalling clock never crosses. It slows, reddens, and freezes at the boundary forever. The frozen star of Soviet astrophysics, the asymptotic approach to a threshold that, in Schwarzschild coordinates, lies an infinite coordinate time away. Both descriptions are correct. Neither is more fundamental. The universe contains both simultaneously in the same equations. Inside, the geometry has transformed. The radial direction inward has become time-like. The singularity not a place to avoid, but a moment in the future toward which every possible path converges, as unavoidable as tomorrow. Stephen Hawking's 1974 work showed that black holes emit faint thermal radiation through quantum processes near the horizon. Jacob Bekenstein's 1972 demonstration that black hole entropy scales with horizon area rather than volume suggested that everything that fell in is encoded on the boundary surface, the seed of the holographic principle of Juan Maldequena's 1997 mathematical duality, of the firewall debate that Almhiri, Marolf, Polchinski, and Sully reopened in 2012. The information paradox remains unresolved. The interior is sealed. The singularity lies beyond the reach of current theory, at the place where general relativity reaches its own edge and asks for a physics not yet written. Across this entire journey, a long conversation about the nature of time ran as a second current beneath the physics. Aristotle, in the 4th century before the Common Era, time as the measure of motion, dependent on a perceiving mind. Augustine, around 400 of the Common Era, time as interior duration, existing only in the present moment of the soul. Newton, in 1687, absolute and universal, the skeleton of everything. Kant, in 1781, a form of human intuition prior to all experience. Bergson, in 1889, and again in his 1922 debate with Einstein in Paris, lived duration, flowing and continuous, distinct from the physicist's measurable coordinate. Einstein, the coordinate, precise and relative, the only kind of time physics can speak to. Barber, in 1999. Perhaps no fundamental time at all, only the correlations between quantum states generating for observers embedded within them the experience of a sequence. The arc of that conversation is the arc of our species slowly, carefully abandoning the certainty that time is simple. It was not absolute. It was never absolute. It was always the specific measurement of the specific curvature of the specific path through space-time. The black hole does not create this truth. It makes it impossible to overlook. Time does not stop near a black hole in any observer-independent sense. What appears to stop from outside is the coordinate time of the distant observer, a bookkeeping device, valid in flat space-time, strained to its breaking point as the curvature deepens. The infalling clock does not stop. The infalling clock crosses, continues, and eventually reaches the singularity, which is not the stopping of time, but the edge of a map that has not yet been extended. The question we started with, why does time stop the closer we get to a black hole, turns out to have been built on a premise the physics has gently and completely dissolved. The black hole is not a place where time ends. It is the instrument that reveals what time always was. The wristwatch on your arm is not keeping an approximation of universal time, a locally convenient fiction that differs from some deeper cosmic standard. It is keeping the only kind of time that exists, the proper time of this path, in this gravity, at this altitude, on this planet. Every tick of its mechanism is a real measurement of the curvature of space-time at this location. Every second it marks is a second of genuine duration, along a world line that belongs to no other body in the universe. The hook opened with a wristwatch. It called that watch a kind of time that exists nowhere else in the universe. At the time, this was a claim about the problem, about how the watch would disagree with other clocks near the black hole. Looking back from here, it is something else. It is a description of a feature, not a flaw. Every clock keeps a kind of time that exists nowhere else in the universe. That is not a limitation of clocks. That is what time is. There are things we cannot know. The interior of a black hole is sealed by the geometry of space-time from all outside observation, not temporarily, but permanently. The singularity's true physics remains beyond the reach of any complete theory. The information paradox is unresolved. Some questions are structurally unanswerable from where we stand, built into the causal architecture of the space-time we inhabit. The melancholy of that is real. Honoring it is part of honest understanding. And yet, the universe was under no obligation to be knowable at all. That a species on a small rocky planet could trace the geometry of space-time to the event horizon of a black hole, could derive, from first principles and confirmed experiment, the precise ratio at which time runs at 1.5 Schwarzschild radii, could describe in mathematical detail why the outside observer sees the infalling clock freeze and the inside observer sees it continue, could image the shadow of a supermassive black hole 26,000 light-years away with a telescope the size of the Earth, is not something the universe was required to permit. It is something that was found, earned, built equation by careful equation, from Newton's river to Einstein's curved dimension, to Pound and Rebka's 22-meter tower, to the Event Horizon Telescope's 2022 portrait of Sagittarius A star. The knowing, in the end, is its own form of extraordinary. If this changed how you think about time, about the watch on your arm, the gravity beneath your feet, the stars overhead, the specific and irreplaceable corner of the universe's geometry that you inhabit, then the time was well spent. Thank you for traveling this far, for staying with the question through all its layers and complications, through every place where the comfortable picture dissolved and something stranger took its place. It is not a question that rewards impatience, and you were patient with it. The wristwatch on your arm will keep ticking when you set this down. It will keep its honest, local, specific time in the gentle curvature of a planet's gravitational field, on a world line that no other clock in the universe is following. Somewhere, 26,000 light-years away, Sagittarius A star is bending space-time around its 4 million solar masses, and time near its horizon is running at a fraction of the rate it runs here. Both clocks are correct. Both are keeping the only kind of time there is. That is enough. That, it turns out, was always enough.